When you feel sick, you usually pull a thermometer out of the medicine cabinet.
Right. Yeah. First thing you do.
Yeah, you put it under your tongue, you wait a minute, it beeps, and it says, I don't know, like 101 degrees.
Mm-hmm.
And you think, okay, well, I'm sick. But that thermometer, it doesn't actually tell you if you have a bacterial infection or a virus or, if you just sat in a sauna for way too long.
Exactly. It's just a number.
Right.
Yeah.
It only gives you the symptom. It doesn't give you the underlying disease. And for decades now, that is exactly how we've been talking about climate change.
Yeah, it's a huge problem.
We just obsess over the global temperature, right?
Okay.
The thermometer reading.
Mm.
And we treat it like it's the whole story.
Which is a fundamental misreading of the physical reality of our planet. I mean, temperature is really just the end result. It's the very last step in the chain.
Okay, let's unpack this, because the sources we're looking at today are pretty mind-blowing.
They really are.
Yeah, they say that if you only look at the warming air, you are completely missing the colossal, invisible mechanical gears that are just turning behind the scenes.
Right, the real engine of it all.
Exactly. So today, we're basically throwing away the thermometer. We're taking a deep dive into Earth's actual accounting books.
But not dollars and cents.
No. We are tracking planetary energy. And to understand an energy budget, we have to start with a surprisingly simple analogy from today's sources.
The planet and the heater.
Yes. So imagine Earth is just this rock sitting in the dark, and it receives all of its income, all of its energy from a giant external heater.
The sun, I mean, it is the ultimate source of almost all energy in the Earth system.
Right.
The sun acts as this massive cosmic heater, and it pays our energy, our income, in a very specific currency, which is shortwave radiation.
Shortwave. Okay, so what does that actually mean in plain English?
So we're talking about visible light, ultraviolet light, near-infrared radiation. These are tight, fast energy waves.
Right, in fact.
Yeah, and they travel through the complete vacuum of space, completely unimpeded, and they just slam into the Earth.
Wow. I'm just trying to picture the sheer scale of that. I mean, we were just constantly bombarded by this giant heater day in and day out.
Every single second, yeah.
But wait, if that's the case, shouldn't we be boiling? Like, why hasn't the Earth just kept heating up forever until the oceans vaporize?
Well, that is the secret of the planetary energy budget. See, Earth isn't just a passive receiver.
Okay.
It actually has to act as its own heater. To survive, the energy in from the sun has to be perfectly matched by the energy out.
So it has to get rid of it.
Exactly. Or that's to constantly radiate energy back into the freezing void of space. But here's the catch.
Okay.
Earth is drastically cooler than the sun, right?
I would hope so, yeah.
Yeah, so because it's cooler, it can't emit those tight, fast, shortwave visible light waves.
Right, like the Earth isn't glowing in the dark like a star.
Exactly. It's not a star. Instead, it emits long-wave radiation, which we physically experience as infrared heat.
Oh, I see.
So shortwave light comes in from the sun, and long-wave heat goes out from the Earth.
Okay, that makes sense. Shortwave light in, long-wave heat out.
Right. But before the Earth even gets to process that incoming solar income, it actually has this built-in defense mechanism.
Oh, right. The sources talked about this. It rejects a massive chunk of that energy right at the door.
Yeah, it's a property called albedo.
Albedo. So that's basically the reflectivity of the planet, right?
Yeah, think about walking across a black asphalt parking lot barefoot.
Oh, in the middle of July. Yeah, it's awful.
It burns your feet, right?
Yeah.
But if you step onto a white concrete sidewalk, it's fine.
Yeah, it's way cooler.
Exactly. The dark asphalt absorbs the sun's rays, and the white concrete reflects the light away. Well, Earth has its own parking lots and sidewalks.
Okay, so what's an Earth sidewalk?
Bright surfaces. So the massive ice sheets in Antarctica, the sea ice in the Arctic, even dense, bright cloud cover. They have a very high albedo.
So they're the concrete.
Right. They reflect about a third of the incoming solar radiation straight back into space, like a giant mirror.
Wow. A whole third.
Yeah, roughly a third. That energy never even enters the Earth's budget.
Yeah.
It just bounces off and it's gone.
That's crazy. Okay, so then the dark surfaces, I'm guessing like the deep blue of the open ocean or, dense green rainforests.
Right, or exposed dark soil.
Those are the asphalt parking lot. They absorb that solar energy and they actually warm up.
You nailed it.
Yeah.
And that absorbed energy, that is the engine of the entire Earth system.
Yeah.
I mean, it drives the ocean currents, it fuels our weather systems, it powers photosynthesis, it does basically all the work of keeping the planet alive.
And then eventually, all of that absorbed energy is transformed, right?
Yeah, it's transformed and re-emitted by the Earth as that slow, outgoing, long-wave infrared heat we just talked about.
Okay, let's pause here because this actually creates a paradox for me.
Okay, hit me.
If the giant heater pumps shortwave energy in, and the Earth eventually radiates the exact same amount of longwave energy out into space,
Then the budget is perfectly balanced.
it should be, yeah.
So why is the planet warming? Like, where is the bottleneck in this entire system?
The bottleneck is actually the atmosphere itself, or specifically a very tiny fraction of trace gases floating in the atmosphere.
Okay, the usual suspects, right? Carbon dioxide, methane.
Nitrous oxide, water vapor, yeah. The greenhouse gases.
So let me see if I have the mechanics right here, based on the notes. Is it almost like a one-way mirror?
How do you mean?
Like the shortwave light from the sun slips right through the glass coming in, but when the Earth tries to radiate its own long-wave heat back out, these gases act like a mirror and reflect it back down.
So you're on the right track regarding the end result, but the actual physical mechanism is completely different.
Oh, really? It's not a mirror.
It's not like a mirror at all, because greenhouse gases don't actually reflect heat. You want to think of it more like a heavy down blanket on your bed?
Okay, a blanket. Right. A blanket doesn't reflect your body heat. It absorbs it. It traps it close to your skin instead of letting it escape into the cold room.
Huh. So how does an invisible gas act like a heavy blanket?
It all comes down to molecular geometry. It is a purely physical, structural thing.
Wow.
Okay? Yeah, the molecules of these greenhouse gases are structurally complex. When the tight, fast, high-energy shortwave radiation from the sun comes in, it just passes right past these molecules.
You don't even interact with it.
Exactly. The gases just completely ignore the shortwave light.
Okay.
But when the Earth tries to radiate that slow, wide, sluggish, long-wave infrared heat back out,
The outgoing stuff.
right, the greenhouse gas molecules are the exact right size and shape to catch those specific waves.
Oh, like catching a slow pitch in baseball.
Yeah, that's a great way to put it, yeah. Catching a slow pitch. And when a CO2 molecule catches that long-wave heat, it gets excited.
It gets excited.
Yeah, in a physics sense. It starts vibrating violently.
Yeah.
And as it vibrates, it bumps into other molecules in the air, transferring that thermal energy.
I see.
It absorbs the heat, it holds on to it, and then it radiates it in all directions, which includes bouncing it back down toward the surface.
And that is the greenhouse effect.
That is the greenhouse effect. And what's fascinating here is a crucial point from the sources that honestly often gets lost in the public climate debate.
Which is what?
This is a completely natural, utterly vital planetary process.
Vital. I mean, I feel like we spend all our time talking about greenhouse gases as this massive existential threat, not a life-saving feature.
Oh, absolutely.
Huh.
But without that natural down blanket of greenhouse gases, the Earth's average surface temperature would be near 0 degrees Fahrenheit.
Wow, 0.
Yeah, it would be a frozen, completely dead rock. The oceans would be solid ice.
So the natural greenhouse effect is literally what makes Earth habitable.
Exactly. The crisis we face isn't that the greenhouse effect exists.
Right. The crisis is that we are adding more feathers to the blanket.
Yes, we are basically pulling a heavy winter duvet over a planet that only really needs a light spring quilt.
Which naturally pivots to, well, the million-dollar question.
Right.
If this blanket kept our climate perfectly balanced for literally millions of years, what changed? And according to this deep dive into these planetary boundary notes, to understand the change, we actually have to look underground.
We do. We have to look at the carbon cycle, but we have to divide it into two very different gears.
Okay, 2 gears.
There is a fast gear and a slow gear. The fast gear is biological. You know, a tree grows, it pulls CO2 out of the air. The tree dies, it rots, it releases the CO2 back.
Right, that budget is balanced on a normal human timescale.
Exactly. But the slow gear is geological.
Geological meaning deep time.
Deep time. Hundreds of millions of years ago, massive swamps and these primordial forests absorbed immense amounts of solar energy and atmospheric carbon.
Okay.
And when those plants died, they didn't just rot on the surface. They fell into these oxygen-deprived swamps. They got buried under layers of sediment, and over immense, unimaginable epochs of time,
Heat and pressure just crush them.
crushed them into coal, oil, and natural gas.
They are literally buried sunshine. I love that phrasing. It's ancient compressed carbon that the planet safely locked away in a subterranean vault.
It's perfectly put. And once it was in that vault, it was completely removed from the active atmosphere.
The planet moved on.
Right. The planetary energy budget adjusted to a world with much, much less carbon in the sky. It cooled down to a stable point.
And then in a geological blink of an eye, I mean, just a couple of centuries ago, humanity invents the steam engine.
Yeah, we figure out how to break into that geological vault.
We dig up hundreds of millions of years of stored carbon, and through combustion, we just forcefully inject it back into the active atmosphere in a matter of decades.
Exactly. We were transferring carbon from the slow underground geological reservoir into the fast above-ground atmospheric cycle.
At a speed that natural planetary processes just simply cannot handle.
Not even close.
And here's where it gets really interesting, because this leads to a concept in the notes that totally rewired how I view our climate goals.
It's a stock and flow-ish.
Yes. The distinction between an emission, which they call a flow, and an atmospheric concentration, which they call a stock.
Honestly, the stock versus flow dynamic is arguably the most misunderstood aspect of climate science by the general public.
It really is. So let me try this analogy out. Think of the atmosphere as a giant bathtub.
Okay, a bathtub.
Our annual greenhouse gas emissions, all the exhaust coming out of our tailpipes, the smoke from coal plants, the methane from agriculture.
Right.
That is the water flowing out of the faucet into the tub. But the atmospheric CO2 concentration, the actual total amount in the air, that is the water level sitting in the tub.
And this is exactly where the public discourse gets incredibly confused.
How so?
Well, you will see headlines celebrating that, global emissions dropped by a tiny percentage one year, or that a country flattened its emission curve.
Like, oh, emissions are down 2%.
Right. And people read that and think, great, we fixed it. The problem is going away.
But it's not.
No, because if you just turn the faucet handle back a millimeter, the water's still pouring in.
The tub is still filling up.
But the tub is absolutely still filling up, just slightly less fast.
Wow. So the climate doesn't actually care how fast the faucet is running. It only cares about how much total water is in the tub.
Precisely. Even if we cut our emissions in half tomorrow, which would be a monumental achievement,
Right.
we are still adding water to a tub that is already overflowing.
That is such a crucial distinction.
It is exactly why planetary boundary scientists don't use annual emissions as their main metric for danger.
Oh, they use the stock.
Yeah, they use atmospheric CO2 concentration as their actual control variable because it measures the actual physical burden we've placed on the system.
It tells us how heavy that down blanket has become.
Exactly.
So, okay, if the atmospheric bathtub is filling up and the blanket is getting heavier, catching more of that slow, long-wave heat we talked about, what is the actual physical metric scientists use to measure that stress? Because the notes introduce a term here that sounds very, very academic. Radiative forcing.
Yeah, radiative forcing. It sounds dense, but it is the beating heart of planetary mechanics.
Okay, break it down for me.
Simply put, it is the measurement of the imbalance between the energy coming in from the sun and the energy escaping back to space.
The budget deficit, basically.
Exactly. When we thicken the blanket with greenhouse gases, less energy escapes. We force the Earth to retain more heat. That creates what scientists call a positive forcing.
Okay, so positive forcing means warming. It's adding heat to the system.
Yes, but here is where the science gets beautifully and honestly terrifyingly complex.
Uh-oh, I don't like the sound of that.
Well, because burning fossil fuels doesn't just release invisible carbon dioxide. Industrial combustion also releases massive amounts of physical pollution.
Oh, right, like aerosols, sulfates, smog, ash.
Yeah, the stuff that actually makes the air look dirty over a city.
So how does that factor in?
Well, those microscopic aerosol particles, they interact with sunlight too.
Yeah.
But unlike greenhouse gases, which operate on the long-wave heat leaving the Earth,
Aerosols operate on the shortwave light coming in.
you got it. They act like millions of tiny little mirrors suspended in the atmosphere.
Wait, so they bounce the incoming solar radiation back into space before it can even hit the ground.
Exactly.
So while the greenhouse gases are trapping heat and creating a warming effect, a positive forcing, the actual physical pollution, the smog, is blocking the sun and creating a cooling effect.
A negative force.
Oh.
Yes. The Earth's energy budget is currently caught in this massive global tug-of-war.
That is wild.
We are pulling a heavy thermal blanket over the planet, but at the exact same time, we are putting up this massive dirty umbrella that blocks the sun.
Okay, wait. If there are all these competing factors, right? You've got greenhouse gases warming things up. You've got pollution cooling things down. You mentioned earlier changes in the ice altering the albedo.
Right, the reflectivity.
Why not just use the global temperature then? I mean, if it all just nets out into a warmer world, isn't the thermometer still the best tool to measure the danger?
Well, this raises an important question, and it takes us right back to our opening problem. The difference between a driver and a response.
Okay.
Global mean temperature is just the response. It is the symptom of all these competing forces. Radiative forcing is the actual driver.
So looking at temperature hides the details.
If you only look at the temperature, you are completely blind to the actual mechanics of the crisis.
Can you give me an example of how looking only at temperature would, like, actively blind us to what's happening?
Absolutely. Let's use the aerosols we just talked about.
The dirty umbrella.
Right. Let's say humanity miraculously switches to 100% clean renewable energy tomorrow.
Okay, best case scenario.
We shut down all the coal plants, all the diesel engines. We completely stop emitting CO2. That is fantastic for the long term.
Huge win.
But we also stop emitting all the smog and all the aerosols.
Oh.
The tiny mirrors literally fall out of the sky.
Because there's no more smoke.
Exactly. The umbrella disappears within weeks because rain washes aerosols out of the atmosphere very quickly.
But the CO2...
The CO2, the heavy blanket, stays in the atmosphere for centuries.
Oh, wow. So suddenly the full unshielded force of the sun hits the Earth, and the blanket is still there.
And the planet rapidly warms. The temperature actually spikes, even though we did the right thing by cutting emissions.
That is terrifying.
If you only look at the thermometer, you'd think clean energy made things worse.
Right. You'd say, turn the coal plants back on. It was cooler.
Exactly.
Yeah.
But if you look at radiative forcing, you understand you're just revealing the true heat imbalance that the smog was hiding all along.
So the pollution is literally masking a huge portion of the warming we've actually caused.
It is, yeah.
That brings up another really unsettling thought. If this massive tug of war is happening and the Earth is retaining all this net positive energy, where is the heat actually going?
That's the big question.
Because I look at a weather app and, you know, the air is maybe a degree or 2 Celsius warmer than it used to be. That doesn't seem like enough to represent a massive planetary energy crisis.
And that is the ultimate illusion of the thermometer. See, the atmosphere, the air around us, is incredibly thin. It actually has a very low heat capacity.
Okay, so it can't hold that much heat.
Right. The vast, overwhelming majority of the trapped energy from our positive radiative forcing, I'm talking over 90% of it.
90%.
Over 90% of it is entirely hidden from your weather app.
Where is it?
The oceans.
The oceans?
Water is dense, and it can absorb a staggering amount of thermal energy without actually raising its own temperature very much.
So the deep oceans have basically been acting like a massive planetary sponge.
A sponge soaking up the brunt of this entire energy imbalance.
So in a weird way, the oceans are doing us a huge favor. They're hiding the heat from us.
Temporarily, yes, but physics demands a reckoning.
What does that reckoning look like?
Well, as the oceans absorb that colossal amount of heat, the water physically expands. Thermal expansion is a massive driver of sea level rise, completely separate from melting ice caps.
Just the water getting warmer makes it bigger?
Yes. And that hidden heat is also violently altering global ocean currents. It's starving marine ecosystems of oxygen, and it's basically loading the dice for catastrophic supercharged hurricanes.
Because the energy has to go somewhere.
Exactly. The energy is in the system. The fever isn't just in the thin air. It has penetrated deep into the actual bones of the planet.
Man, it is so deeply unsettling when you frame it that way. It's a systemic energy balance problem, not just, you know, a summer day getting slightly hotter.
Right.
Which brings me to what I think is the critical question for our listeners. Let's say someone is driving to work right now on a Tuesday, or they're prepping for a board meeting. Why does this abstract planetary ledger matter to them? Why is this energy imbalance strictly defined as a planetary boundary?
Well, we connect this to the bigger picture. We have to zoom out and look at geological history.
Okay.
The modern world, and I mean literally everything, every wheat field, every coastal city, every global supply chain, the stock market, our legal institutions.
Everything we know.
It was all built during a very specific, remarkably quiet geological epoch called the Holocene.
The Holocene, which started about, what, 10, 12,000 years ago?
Right at the end of the last ice age. And the Holocene is characterized by one miraculous feature.
Let me guess. An incredibly stable planetary energy budget.
You got it. The temperature barely fluctuated. The seasons became ruthlessly predictable. The monsoons arrived on schedule every single year.
And because the climate was predictable, humans could finally settle down and invent agriculture.
Exactly. You cannot plant massive fields of crops if you don't know when the rains will come or when the first frost will hit.
Right, you'd just starve.
Agriculture requires a stable energy ledger. Our sea level ports require a stable ocean volume. We built the entire scaffolding of human civilization on this foundational assumption that the Earth's energy budget would simply never change.
And now, by digging up the ancient geological carbon and stuffing it into the fast atmospheric bathtub,
We're taking a sledgehammer to that scaffolding. We are pushing the Earth system away from that stable Holocene state.
And the notes point out that the danger of breaking a planetary boundary, it isn't just a slow, linear decline, right?
No, the danger is tipping points.
Thresholds where the system just flips.
Yes, where the change becomes self-reinforcing. Think back to the albedo effect we discussed.
The reflectivity, right?
As the world warms, the bright white sea ice in the Arctic melts.
Which takes away the white concrete sidewalk.
Exactly. And that exposes the dark, deep ocean underneath, the asphalt parking lot.
Which then absorbs more solar heat.
And that extra heat melts even more ice, which exposes more ocean.
Oh man, a vicious cycle. So once it starts, the planet essentially acts as its own heater, regardless of what humans do with our emissions.
Exactly. The Earth takes over. Or take the Amazon rainforest. If we change the hydrological cycle enough, the rainforest dries out and literally turns into a savanna.
And all those trees die.
When those billions of trees die and rot, they release their stored carbon into the atmosphere, which further thickens the blanket. We risk triggering this cascade of dominoes that pushes the Earth into a completely different, much hotter state.
A state that is fundamentally hostile to the agricultural and infrastructural foundations of modern society.
That's the real threat. It's about maintaining a planet that can support us.
So what does this all mean for us today? Because, the sources we're analyzing make a very deliberate point not to frame industrialization as just this massive mistake or some evil plot.
No, not at all.
The goal isn't to repent and, return to the Stone Age.
The notes are actually very pragmatic about this. Fossil fuels provided the incredibly dense, reliable energy that literally built the modern world.
Right.
They powered unprecedented leaps in human well-being. I mean, we have modern medicine, mass sanitation, global transportation, indoor heating, mechanized agriculture.
All because we tapped into that ancient subterranean energy vault.
Exactly. The problem isn't the energy itself. It's the biological cost of the carbon exhaust.
So the challenge of our century is to basically decouple human progress from carbon extraction.
Exactly. And the text mentions the framework of donut economics, which I think visualizes this perfectly.
Oh, I love this concept. Let's explain it.
So imagine a donut. The inner ring of the donut is the social foundation. People need energy for hospitals, for schools, for homes. We can't let people fall into the hole in the middle.
We can't go backward on human rights and living standards.
Right. But the outer ring of the donut is the ecological ceiling. We can't expand our energy use so much that we shatter the planetary energy budget and trigger those tipping points we just talked about.
So we have to live in the dough.
We have to live in the dough. We have to transition to low-carbon industrialization. We have to learn to harvest our energy directly from the fast-moving, real-time flows of the Earth system.
So solar, wind, geothermal.
Exactly. Instead of burning up the slow, compressed geological vaults of the past.
We have to turn off the faucet so the atmospheric bathtub stops filling.
And so the energy budget can slowly, eventually find its balance again.
It is just such a profound paradigm shift. I mean, honestly, next time you look at a weather app, don't just see a temperature.
It's so much more than that.
Try to visualize this incredibly fragile, dynamic planetary ledger. The invisible shortwave light slamming down from the sun, the slow rolling infrared heat trying to escape.
The bright ice caps reflecting light away.
And that chemical blanket we are actively weaving in the sky.
Sure.
It is really a masterpiece of physical mechanics.
It truly is. Once you see the world through the lens of energy flows, you really can never go back to just looking at a thermometer.
You really can't. Which brings me to a final, honestly slightly haunting thought that I want to leave you with today.
Ooh, lay it on me.
When scientists calculate all this radiative forcing, right, all this energy imbalance, they have to measure it against a baseline.
Right, starting point.
A starting line for a stable, safe Earth. And the notes mention that they use the year 1750 as that baseline.
1750.
Think about that for a second. 1750, before the very first steam engine fired up. Before we started digging up millions of years of buried sunshine.
Wow.
If our planetary safety zone, the literal baseline for human civilization, is anchored to a world lit by candles and powered by windmills.
Yeah.
How far past the physical threshold are we right now?
This is a sobering thought.
Something to mull over until next time. Keep questioning, keep exploring, and we'll catch you on the next deep dive.